Hi everyone, welcome back to the faculty presentation seminar or series in the seminar. Today we have Dr. Paquita Zuidema, someone who has made outstanding contributions to the field of atmospheric sciences, and as a result was recently named the 2024 Fellow of the American Meteorological Society. She joined UM in 2005 and is now a professor, an avid seashell collector, and the department head of atmospheric sciences here. Without giving away too much of today's presentation, the Zuidema group studies cloud processes, their radiative impacts, and relationships to the large-scale environment. So thank you everyone for coming and enjoy the series.
Great. Well, thank you for that nice introduction, Rachel. This is a photo that Tyler, Michael, Sam, and I took just before this seminar, and I realized that minus one person, we may have the tallest research group in ATM. I just felt like a midget. So that was something I've learned today. I want to express my gratitude to the Compass seminar, and really, I say this with all sincerity, but working with the students as in the time that I've been here has really been like the most satisfying, most rewarding part of being a professor. Just getting to interact with them on research questions, and they've really helped guide me on what I actually get done as opposed to what I would like to get done. So it's really been something I'll take with me through life, the rest of my life. So besides Tyler and Michael and Sam, there's also Amy, who just defended last week or a week ago, and two other people that have worked remotely mostly. Isabel McCoy was a postdoc who spent the pandemic in New Mexico, and Seethala Chellappan, her name's underneath that sign, is an assistant scientist who also mostly works remotely. So the questions that have motivated my whole career are these two. What explains the life cycle in low clouds from its initiation, development to its death, and how does that impact the net radiation field? So you have this is the net radiation from a year's worth of series data, net cloud radiative forcing. In the sun, we have about a net negative. Clouds provide a negative impact on the radiative climate, and it sort of maps onto where you have most of the low clouds. So, and there keeps being more and more, there's still a lot to do in this area. So how did I get there? I mostly grew up in a small university town with a large university in central Illinois, Champaign-Urbana. My father was an anthropology professor there, so we moved there when I was 8 from the Netherlands via Peru, and I ended up staying there for college. My grades actually weren't that good in high school, and I thought I would need to go to community college for a while first, but I applied and they let me be a landscape architecture major for a year, and I got my grades up and ended up doing science. I kind of thought I wanted to do something with a little more social relevance, so I tried public policy. It didn't really suit me. I missed science, so I went to Seattle, and I happened to be next door to the atmospheric sciences department there, and that turned out to be a life changer for me. I ended up transferring into that program, and I met Brian there, and that has kind of set the course of my life, my career. So this is what I did for my master's project there, and I'm still working on the same stuff, really, as I started then. My advisor had me look at IRBI data in relation to microwave satellite liquid water path to look for that relationship and fit it with a model. So that seemed like it should be pretty straightforward. You know, I mean, this would have been the early or mid 90s or so. And sometimes it worked and sometimes it didn't. And it really vexed me that it didn't always seem to work. And I really kind of felt like I failed my project. I didn't quite realize how hard it was at the time. So that just made me kind of motivated to try to, figure out what the problems were and why this wasn't such a nice fit necessarily. So Brian and I got married. We moved to Boulder, and you can't. I don't think you can see it underneath. It's my PhD advisor there was somebody named Frank Evans, who is a very brilliant scientist, I thought. He is. And we looked at, and he had this really nice three-dimensional radiative transfer model there, so everything was really worked out. And what I took away from that project, so we looked at cloud radar data that was resolved into an extinction field where you had all the the details on the cloud extinction coefficients. And what I took away from that is that, well, if you specify the cloud correctly, you can do pretty well with pretty simple radiative transfer models. You don't really need to do the whole fancy 3D RT thing. So, and it also exposed me to instrumentation that was just coming online at the DOE ARM sites, or atmospheric radiation measurement sites. So Boulder had one of the NOAA labs there. At the time it was called Environmental Technology Lab. So they were like a test bed for new technologies, mostly remote sensing. And I wanted to learn more about these techniques. So I did an NRC postdoc there, and I got to work on data from the Arctic. So something called SHIBA, surface heat energy budget of the Arctic. A lot of new data was coming out from that, and something that I found really satisfying was I did a case study on this really long-lived mixed phase cloud. So mixed phase is a combination of ice and liquid in the same cloud, only has to exist at below 0 Celsius, and just looked at that life cycle and how that impacted the radiation. And the liquid mostly sets the cloud albedo, but the ice has a large influence on what how long the cloud lasts. So it's so they're both important. So that was pretty neat. But then moved down here to Miami and thought, all right, I'm going to focus, be an assistant professor, try to get tenure, try to be relevant to my new environment, and look at shallow marine clouds, and try to understand and look at the research frontier in those processes. So one thing that came along pretty soon after I got here was I heard about a campaign in the Southeast Pacific called Vocals, right offshore of Peru. So I thought that was great to be able to go back to that part of the world. And its focus was on trying to understand how and why overcast stratocumulus clouds break up in that region. So microphysicists were enthralled with a phenomenon called pockets of open cells, where in the middle of a thick stratocumulus deck, the clouds will, for no reason it seems like, just kind of break up into these open celled structures that have much lower cloud albedos. So that was the focus of that campaign, and what I did for that, let's see, okay, and I was able to recruit my first student, David Painemal from Chile, who was a great pleasure to work with and is now doing quite well as a leader himself of a cloud group. And what we did, and what I proposed to do, was to put microwave radiometers on both an airplane and a ship, and just like really nail the liquid water paths for this region, because that's because the albedo is so dependent on those values. So I leased something from a company called ProSensing. It looks like this. It's at the time I leased it for this field campaign, put it on the plane. It's it looks like a little rocket or something. It's about 3 feet long, about maybe this big. It's not that big, and it looks up into the sky. So you have to fly below a cloud. You look up, and you measure. You get these brightness temperatures that tell you something about how much water vapor and liquid is in the sky above you. And another noteworthy thing, it was developed for the Arctic, so it's not that sensitive to ice. So it's really good for mixed phase conditions, but could also be applied here. And I'm going to come back to this again. So this instrument's kind of a recurring theme in this talk. It turned out, it was an NSF experiment, but the conditions were just so great for looking at kind of standard remote sensing retrievals of cloud optical depth and effective radius. And there's a bit of a cultural disconnect, maybe not so much now anymore, but where the satellite scientists, they're concerned about optical depth, so it gives you, that relates more directly to the cloud albedo and the effective radius at the cloud top, whereas cloud scientists are more interested in like cloud droplet number and liquid water path. So, people had been looking at conversions between these two for a while, but David and I wrote, this paper with a fairly humble title of just like integrating the different data sets that we had to see how well you could apply the satellite retrievals to be able to do like a larger scale assessment, because it's a really simple formula. It just has those 2 input parameters with a constant in it, and it worked. It worked really well. So I feel I take some pride in kind of setting, opening up an area where people can do more work with confidence now, looking at satellite retrievals of cloud properties. And he did other work too, looking at how albedo and precipitation varies with liquid water path. That was more, not just assessment. So around that same time, let's see, when I came down here, NOAA had a project going on in the Caribbean called Rain and Cumulus Over the Ocean, and they asked me if I wanted to be chief scientist on that. So I was like, yeah, that sounds great. And this was the question that they were going after. How do you get rain to develop so quickly in marine cumulus? So I have a couple of schematics there taken from Wallace and Hobbs that I teach in my class. It's in cloud physics you learn a very kind of one-dimensional model of life, like where you have an updraft, the cloud develops, some microphysics things happen, and it's all just happening in a column. So that's what I teach in that class. But going out there, so it was actually a lot went wrong on that campaign. The little this boat I was on was called the Seward Johnson. It's not. I think it was the last trip I ever did. It was out of Fort Pierce, and and a lot of instruments didn't work. But we were there kind of at the right time, at the right place. Well, the 2 weeks that we were out there, it rained a lot, and it was clear, like just from being there, that the rain rate was connected to dynamics. Like it was happening at the edge of what we call cold pools, where there's rain evaporation, the air temperature cools, but there's also downdrafts that are actually bringing down drier air, so the air is not, theta E is actually going down with the rain rate. So that was pretty interesting, and not something I'd learned in class or anywhere. And if you looked at satellite data, if you overlapped this with radar, all the rain was happening on the edges of these arcs. So that it was, it's obvious if you look at satellite imagery, but it wasn't, it just wasn't in the conceptual thinking so much. So it took, I wrote proposals, and it was Shujun Lee ended up working on this project. It actually took a while to have time and funding to get back to look at that data. But this is the paper that I really wanted to write that came out of it, and it's kind of, it turned out to be very good for, it just kind of opened up more research and a different way of looking at how trade cumulus clouds are organized. And so that's kind of kept on going. There was a big project just a couple of years ago called Eureka Atomic that really focused more on mesoscale organization of shallow clouds and how that interacts with climate. If you have more aggregated, more clumped together clouds, that will have a sort of a net. It will reduce the total radiation, shortwave radiation associated with it. So that's something Isabel worked on for her postdoc and still is. We're still doing work with these data sets. And Michael is also working with those data. And what we're trying to understand now is, I was really struck, I don't know if you can tell, but there were these huge expanses of cloudless areas, and it's not something you notice in Miami. Here there's always some cloud around, but in the western tropical Atlantic, you could look off the ship and just not see any cloud for large distances. So we are using there's a motion stabilized Doppler lidar on the ship, which is pretty nice form of technology that you can get the vertical velocities, and it's not too disrupted by the ship motion. And so we're this is kind of an old problem. How do you get the initial cloud development to happen, these smallest clouds? But with this new technology, we think they have something that we can add to that. Okay, so that was so that's the trade wind regions. After that vocals project ended, I got drawn to the Southeast Atlantic region. It's not only is there a large stratocumulus deck there, but it's also right next to the African continent, where you have they're mostly agricultural fires, but they release about 50% of the global carbon emissions on the planet. So fires are becoming a bigger deal in the U.S., but there's actually a lot more carbon being emitted, or smoke being emitted off of Africa than in the U.S. Still. So figured, if there's going to be an aerosol cloud interaction anywhere, it's got to be in that area, because there's just so much aerosol coming off of these fires. So this would have been right after vocals, and there hadn't been that much field work in that area, so I just kind of focused on it and started learning and writing proposals to do work there, engaged with vocals people. So I guess I got a little more ambitious after that vocals campaign, and I wanted to learn more about the large scale influences as well as the microphysical. So I was involved with US Clygar, and when this is a multi-year satellite analysis, but one thing that really struck me was it's comparing the Atlantic to the Pacific stratocumulus regions. I just thought it was interesting that there's a lot of similarities, but the cloud fraction in the Atlantic has a much more pronounced seasonal cycle than the one in the Pacific, even though the SST and the LTS is lower tropospheric stability. They kind of vary vary in similar ways. AOD stands for aerosol optical depth, so that's showing that one area is clean and one region is clean and the other has those fires. So there was just like a lot of interesting questions about that region, and also I also thought the meteorological coupling over that Atlantic basin had to be a lot more pronounced than it would be over the Pacific because it's just a lot smaller. I happened to be at this meeting kind of by chance. I think I was in Europe, and I don't usually go to this meeting, but it turned out to be a very, there was a lunchtime gathering where people were kind of talking about trying to figure out the aerosol radiative effect, and that kind of was the germ for like we called ourselves an international working group. It's really just a big name for some email correspondence. So this was kind of a question at the time. Like, you have these leading models, global aerosol models, and over this region, you actually have a wide range of the net radiative impact. It can be either cooling or warming. And if you look, like, this is smoke above cloud. I don't know if you can see that there's cloud on the screen there. It's because the smoke is so dark, so you don't quite know what's what. For proposal writing, some worked, some failed, some succeeded. You're only seeing the successes on here. It was a great experience. I worked a lot with the people that are shown here, and kind of just learn more about how to lead field campaigns. So now, and also this is, I got funding over the years to be able to support 4 students through DOE, NASA, and NSF, beginning with Yemi at IUB. So his first, what he looked at, so that this was when we were just starting, was this meteorological coupling between aerosol and the land. How is the aerosol getting over the ocean? There had to be winds that brought it out there, and so he looked into that with just using reanalysis data and the thermal wind equation, basically. But we unraveled, I think, some interesting things about how smoke can enhance its own transport over from further away from its origin. And he also highlighted that there's also a lot of moisture that is advected along with the aerosol, which also matters for the radiation field. So then Jinghao looked at DOE ARM data sets off of this remote island named Ascension, and looked at this seasonal cycle variation asked the question, could smoke be have an influence on the seasonal cycle in the cloud cover? And the answer was yes, that when there's smoke in the boundary layer, even though it makes the individual clouds brighter because of the Toomey effect, because of the smaller drops, it reduces the overall cloud cover, and that's actually the more significant influence. So here what he did, we attributed it to radiation, just that smoke absorbs sunlight and raises the temperature of the boundary layer and evaporates cloud. But this anti-correlation between liquid water path and droplet number is it's actually more global than just where you have absorbing aerosol. It has to do with the drop size. So it's it's starting to go in that direction. So Amy, she just finished her PhD, and what her work focused on was, she was an aerosol chemist, so that was, I learned a lot from her because I had to. I didn't really know much about aerosols per se before that. So her work focused on trying to understand why smoke absorbs more sunlight than you would think per particle. And that is, and why you want to know that is because, again, it affects this top of atmospheric radiative forcing. So now Tyler is, so one thing that we still don't really know is how the smoke is actually getting into the boundary layer. We had this idea throughout the campaign that there was this slow circulation, that while the smoke was slowly subsiding, and that's how it was getting into the boundary layer. But that can't quite be right because there's a time offset between the different months when that happens, and so Tyler is revisiting that, and in the process finding interesting things in how fire emissions and air transport have changed in the last 20 years. So I want to leave that to Tyler because he's going to have talk about that in his own seminars and not steal his thunder on that. So these projects all looked in the large-scale subsiding regions from Hadley-Walker circulation, and but you can also get strong subsidence happening, synoptically. So when you have a rotation around a low, you'll have an ascending region in front of it and subsidence behind it. So those generate large fields of shallow clouds too, and these are garnering interest because so this is actually an example that we had locally in early September from Hurricane Idalia. So it's there was colder, drier air coming from the north, and as it flows south, it's picking up moisture off of the oceans and developing those patterns, but it's capped, so these clouds are not growing very deep. So we had really nice weather in early September. So the radiation biases from these regions generate radiation biases, and this is a paper where he did a composite around the center of the lows, kind of like what people do for hurricanes, and the radiation biases are mostly coming from that type of a synoptic environment. And this has been linked to shortwave radiation biases in the southern oceans. This is something that John Pacillo and Kevin Tremberth first highlighted, that the southern oceans just really pop out on here in the CMEP3 models. and you know, that bias is still continuing. It's actually, there's actually a lot going on that is, well, it's not an easy problem to fix, and it's not, I think maybe people at the beginning thought that it was, I mean, the climate models are tuned to have a global energy balance within the water, so that maybe this reflected an issue somewhere else, but it's, there isn't, you know, truly something microphysical going on there. So yeah, so it's been attributed to something called cloud phase bias, where there is too much ice and not enough liquid. You know, the liquid is what gives you the higher albedo, and that's kind of been revealed by LiDAR and radar data from space. And so yeah, so Seethala and I are looking at, you know, how ice and liquid partitions in clouds that are colder than 0 Celsius using data from Activate campaign. It's aerosol, cloud, meteorology, interaction, airborne campaign. It's something that was done out of Langley, Virginia, and it took place during the pandemic. So that's really kind of remarkable because you know, they're flying these two small planes together. So this was the idea with the campaign, that you have two planes stacked on top of each other. One has a lot of remote sensors on it. The other is doing the in situ measurements. They're both small planes, so they're flying kind of slow, which is good for research. And they just do like tons and tons of flights. Because of the pandemic, it turned out, you know, only a few people were flying. So only a few people did like a lot of the work for this campaign. So I don't know, they did it with grace. And so sadly, so my portion of this was going to be to incorporate a new microwave radiometer. So with focals, I just saw some issues with the radiometer that I had, and one of my colleagues from what was then called Environmental Technology Lab had spun off into a startup company that was making these, and so I'd hoped to incorporate one of his, but it turned out it just took too long. So that part never happened. But we still had the opportunity to participate in the analysis. Tons of flights, a lot of colder outbreaks happened, a lot that were sampled. So really, way more data really than is going to be easy to analyze in the available time. But you know, look, we've selected 8 cases from 5 days, just kind of a little bit randomly, you know, or just ones that looked good. What we already kind of knew from the space-based information is that, you know, the clouds rain, the clouds break up. You can just see that here. This we didn't think, this came later, I guess, but these clouds are also pretty polluted because of the you know, the stuff coming off of the U.S. eastern seaboard. So that makes the droplets smaller, and that delays the initial precipitation. That's really about all you can say actually with aerosols in general, that what it'll do. So what we didn't know, you know, was how the clouds were breaking up, and if the ice was contributing to that. Because a lot of the ideas about mixed phase clouds are that ice breaks up you know, it hastens the transitions. In our 8 cases, we found that, you know, there was lots of ice. There was really no trouble with finding ice in them. So that's this orange. These are the measurements we had, and these are other ones from the southern oceans. IMP. So these are kind of primary ice nucleation. So INP stands for ice nucleating particles. Those are the little aerosols that can generate an ice particle in the beginning. Their numbers are really small. And we found, just copious ice out there. So that might suggest that ice would, break up these clouds. The mechanism that people go to for that is, it's this. You can see it in Miami. This is the figure in Wallace and Hobbes, where if you're at temperatures below zero, the relative humidity right next to the ice particle is greater than 100% relative to the ice. So that from the liquid. So that means the water vapor from the liquid ends up getting kind of sucked towards the ice particle. So that's how these are all liquid droplets here generating this beautiful snowflake, because the water vapor is just going on the sides. And you can see it here in Miami. So that's an example from Rickenbacker Causeway, where we'd had a cold front comes through, this is super cold liquid cloud here, and something had started an ice cloud there. The ice particles grow really fast because they're just sucking up water vapor, and they start to fall out. So that it's decreasing the cloud cover in doing so. So that's how people think, this cloud phase bias works, and that's how. And this process is represented in climate models. So what they do is they kind of tweak this to get the ice liquid fractions that they like. So with all that ice in these clouds, you might think that would be happening with these too, but in fact, that's not happening. They're very bright clouds. There's lots of liquid in them, and there's kind of two reasons for that. One, the droplets are they're small because there's so much aerosol coming off of land, and the updrafts are also pretty strong. So you're just generating liquid all the time, and the ice is actually just kind of along for the ride. It's actually not doing all that much in these. So here where it's breaking up, it's actually because it's raining here, and it's raining because there's so much liquid there that it doesn't really have that much to do with the ice, I don't think. We're not modeling this, so that a modeling study will be able to show that more effectively than this data analysis, but I'm pretty confident that that's what's happening. So that's been that's interesting. It's still going on. So kind of related to this, one of the reasons I wanted to look at colder outbreaks is because of this upcoming field campaign that Sam is going to be involved in next spring, where we're going to look at colder outbreaks off of the Arctic sea ice. So these will be different because it's going to be very clean. There's going to be a lot of snowfall coming out. It's colder, so it's not going to be rain coming out of the bottom. They look kind of the same from space, but the conditions will be different. And now, so I've kind of gone back to my old radiometer and fixed it. And try again with that one, which I think it will work. It's just not as fancy as the one I had originally hoped to use. So Sam's working on, at the moment, like looking at how to get both liquid water and snow water path from these microwave brightness temperatures. And next summer, Michael and I are going to go and look at mixed phase clouds over the Arctic, which is motivated by a less, these will be more quiescent clouds. They're still going to be mixed phase, but here the question is more, the Arctic sea ice is going away, and So one idea is, as the sea ice melts away, the ocean becomes uncovered, that you're going to get more cloud cover, and that's kind of going to compensate a little bit for the loss of the sea ice. But another thing that could happen is a lot of the clouds in the Arctic are thin because it's dry, it's cold, there's not that much water vapor there. If the liquid clouds are thin enough, they could actually warm the surface regardless, because the sun can go through the clouds, but the long wave it still gets trapped by the clouds. So you still get a long wave heating, warming of the surface that could actually contribute to further melting. So that kind of, that depends on details such as how much liquid is there in it, because they have to be thin clouds. And so you can't really do this with space-based data because these clouds are just too thin, and they're liquid, so they don't really pop up on cloud radar data. So the microwave radiometry data is kind of perfect for looking at that issue. So that will be, so I'm confident we'll learn things from this. And yeah, in the meantime, I'm happy to enjoy the warm weather here. So thanks for listening to this, and of course if you ever have any cloud questions, I'd love to hear them. And same with Sam and Michael and Tyler, and if you have any questions right now or any comments or anything, I'm happy to entertain them. Stunned. It is a lot of material, so.
I have a question. I think it's more for Tyler, I guess, about the trend that was mentioned about from the African fire. Can you comment on anything? I mean, you just mentioned that there was a trend. I'm curious to know what is the trend.
Oh, it's Tyler would be the person who can speak most eloquently to it, but it's well, do you want to opine or?
Well, right now globally, just burned areas decreasing, so African fires.
I cannot hear you.
Right now burned area, just as a metric, is decreasing. There's less fires. That's like the first quarter. Yeah. So.
And there's also some compensation between grasslands and forest.
Yeah, and the type of vegetation is burning is slightly different too. It's as land use changes and parts of the Congo are drying, but other parts of the African landscape are different meteorological trends. So it's a mess.
Amy?
Have you looked at fire emissions or aerosol emissions from fires in North America? And are there any cloud trends associated with those?
That's a good question, because there definitely it is trending up. So would you,
I mean, a lot of that is making it out over but it's in the summer forecast, right? So
there's people on this Arctic campaign that are interested in looking at that. I guess what I would expect, for the stuff that really goes off land, smoke is an excellent cloud condensation nuclei, so it's going to kind of brighten the clouds. But there is this sort of compensating thing that happens, that when you have higher droplet numbers, that you get more entrainment of air coming in from above, and it ends up thinning the cloud. So, but I don't know if people have looked at
Do you
that at all.
think that's what explained the discrepancy that you started out with on the albedo versus liquid water pad? The fact that
You mean the project with Dennis, the original? I think that was rain, and we couldn't see it because you can't with. The clouds were raining out, and we didn't have the any way to discern if it was raining or not. Yeah. Cassie?
It's a great talk. My question for thinking about the Arctic for upcoming projects, has there been any consideration of like the changing aerosol populations that we expect with less sea ice? Like for example, there's been more evidence of proglacial dust being emitted from the Alaskan Arctic. There's been more evidence of harmful algal blooms in the Arctic Ocean, which those organisms could be really great ice nuclei.
Yeah.
Has there been that sort of consideration with some of these, what you're going to measure for those field campaigns?
Yeah, so like Paul DeMott and his group are involved with both of them. Carrie Pratt is involved with the summertime one, and Lauren Samora, who used to be a student here from the modeling side. So yeah, because we don't really have I think from now on, anytime there's an opportunity to get more aerosol data, people will jump on it.
Yeah, I just keep thinking it might affect the life cycle question, right? If you have more sources of ice nuclei making it up.
We'll just be out there for 6 weeks. Like, we won't really be able to answer that question, I don't think.
Right.
But yeah, so we do have this idea that you need liquid before you can get ice. So that actually is a motivating question. Like, are you able to get an ice cloud at all without it being liquid first? I'd be pretty surprised, but you never know. Jonathan?
If we wanted to find out more information about these projects, is there like a resource that we can go to?
There will be? You mean the upcoming ones or the old ones?
The upcoming ones.
There will be, but there isn't yet. And I'm responsible for one of them, so and I haven't done it yet. All right, well, thank you.